Hi, and welcome to Lecture 5 of Industrial Electricity. We're going to be covering a few different things today. So this will be a mixed lecture. First we'll review series and parallel circuits. I'd like to introduce the voltage divider and the current divider, which you'll find are easier ways to solve some of the solutions. And then we'll get into magnetics. We're going to start magnetics, which is chapter 6 of the text, and we'll get a start on that today. So first of all, let's look at a series parallel resistor question. In this circuit, we want to solve for R sub t, the total resistance of the circuit. So given this circuit, we have our 4 resistors. And so the first thing we do to simplify this circuit is to draw a box around these 2 resistors here. That's the first step. So then we can combine these 2 resistors as they're actually in series. So we'll redraw the circuit with our so basically the resistance here would be R in the box. We call this the box around the resistors. So R box is equal to 4 plus 8 ohms equals 12 ohms. So let's redraw now a simplified circuit of that. Go up here, one more here. So this would look like this. So we have a, let me change colors here, back to yellow. So we have a 5 ohm, 12 ohm, which is our new value of the combined resistors, and a 6 ohm. So now what we do is we draw that box again around these 2 resistors. So we can say now that we have 2 parallel resistors, and we remember from the last time in your homework how we solve that. So it's 1 over R in the box equal to 1 over 6 equal, a plus. It's a plus sign, plus 1 over 12. So if we use our calculator, if we say 6 inverse plus 12 inverse equal to, and then we inverse that, equals to 4 ohms. So now we can redraw this circuit, simplified once again. So it would look like this. 5 ohms there, and now 4 ohms here. And so we draw another box around, let's see if we got the right, kind of a thin, let's do this. That works a little better. Okay, we'll draw a box around these 2 resistors. And so now what we can say is our total equals, these 2 resistors are basically in series, 5 plus 4, and that equals 9 ohms. So there's a second method to do this, and we can show you how that works. So if we draw a box around these two resistors. We can just say that R equals to 8 plus 4 equals 12 ohms. And then we draw another box around these resistors, so the whole thing here. Okay, so the area in that box, we can say this R equals 6 in parallel with 12. Okay, so then we can draw a box around the whole thing now. And say that R equals 4 plus 5 equal 9 ohms. So we'll show you, basically we'll calculate the parallel resistance just as we did before, and but it's just a simpler way of looking at this thing. Both methods work equally well. I started with the first method because it gave you a practice in drawing schematics, getting familiar with them, and showing you what is being substituted for what. But this is actually a simpler and faster way of solving this problem. Okay, now let's talk about voltage dividers. Let's see here. Here we go. So first we'll talk about a voltage divider with a series circuit. Okay, so we have this simple circuit. We have a power source. We have 3 resistors in series. And what we'd like to do is our objective will be to determine the voltage across the 20k ohm. So put a voltmeter in here, like so. So what we'd like to do here is we'd like the voltage of interest, we'll call that Vx, equals the resistance of interest over our total times Vs, the voltage of the source. This is Vs here. Okay, so RT being the total resistance. So what we can say now is VR2, which is what we're trying to determine here, is equal to 20k over 10k plus 20k plus 30k times Vs. So if you do the math here, that comes out to 33.3 volts. Okay. So be sure to add that formula to your note card. It's called the voltage divider formula. Make sure you have that when you take, for your quizzes and tests you're going to take. Before, you would have to calculate the current in the loop, I, which is I equal to 100 volts over the 3 resistors, 10k plus 20k plus 30k, and that equals 1.6 milliamps. So then we calculate the voltage around R2, across R2. So it's I times R, so VR2 equals 1.6 milliamps times 20K, and that equals 33.3 volts. So we get the same answer in both ways, but the voltage divider is a little easier to get to that answer. The first method is a two-step process versus a voltage divider, which is a single-step process. Now we're going to talk about current divider rule. So we have this circuit, 200 milliamp current source, and we have 3 resistors in parallel. So just like in the voltage divider, we want to compute the current of interest equals RT over Rx times IS. So again, solving our equation here, we have 1 over R parallel equal to 1 over 1200 plus 1 over 2200 plus 1 over 3300 and so this yields our parallel, and I'll let you do it on your calculator, is equal to 629 ohms. So we want to find the current through R2. So R2 equals 629 ohms divided by 2200 times 0.02, and that equals 57 milliamps. So the old way we would have said V sub source equals IR, R parallel equals 629 ohms, Vs equals 0.02 times 629, I'm sorry, 0.2, which equals 126 volts, and then the current through IR2 equals 126 over 2200 equals 57 milliamps. So we get the same result doing it a different way. So be sure to put this formula on your note card. So now we're going to talk about magnets and magnetism, which is chapter 6, I believe, in your text. And magnets and magnetism come in very many forms: transformers, motors, generators, relays, solenoids, and speakers. So without these, life itself would be impossible. So these are really the foundations of industrial electronics. We need all these things, and we're going to start by talking about an induction motor. An induction motor has many things going on. We have magnetics. It's a transformer. We have complex power, which we'll talk about later. And also three-phase power. So we need to explore how an induction motor operates. So So let's first talk about magnetism. So let's talk about a simple magnet. A simple magnet has a north pole and a south pole. It also has magnetic lines of flux that look something like, whoa, got the wrong one here. Oh, that's better. Okay. And then if we take two magnets, like such, and we bring them in close proximity, what do we get? Well, they will attach to each other because you got a north and a south pole. They're opposites, so the magnets will stick themselves together. So it looks like this. And then the magnetic lines of flux will go around the combined magnets, like such. But really, they want to move in this configuration. That's back. So this is the configuration where they're most happy. So it minimizes the lines of flux. They're shorter and more powerful, and the magnets stick together and want to be in this configuration. With this, the flux lines are primarily contained within the magnets, with only a few leaving on the edges. Magnetic lines of flux are like an energy state, if you want to think of it that way, where you have a hill and there's a ball at the top. So this would be high energy, and when the ball rolls down the hill, you have low energy. If you have an iron plate, such as this, and you have a magnet, it will attach itself to the plate. All the flux lines are contained within this, and that's why the magnet and the plate stick together. If the magnet were by itself, the flux lines would emanate around it, as we talked about before, such as this, with the flux lines going around the magnet as such. Magnetic flux lines like to pass through iron more so than they do in air. When the magnet is placed against iron, the magnetic flux lines are in the lower energy state. So how would you describe the magnetic lines of flux in this example? In this example, there's two iron bars with a magnet. So I would say that because the iron bars are on the ends of the magnet, they will contain the magnetic lines of flux. So they won't come out of the ends, but would do this. They'd come out of the sides. Suppose we took out the magnet and made it large chunk of iron. Let's do this. And touch that up a little bit. Whoop. And we put an electrical coil around it. And with the current source. What do we have? We have an electromagnet. If we can reconfigure this such that at the ends, let me do a little erasure here. What we'd find is the magnetic lines of flux will seek the shortest path. So they would extend through the gap of this electromagnet. If we take our piece of iron and put it in a circular configuration like this, and we add coil windings here and here, this magnet, if we look at the magnetic lines of flux, they'll bend, go through here, and what will happen is this will tend to make this rotor, which this is, it's shown as a magnet with a shaft in the middle, that will end up straightening itself out. Let me just erase that so it would look like this, because the magnetic lines of flux would want the path of least resistance, so it would turn this thing so it aligned with the electromagnet. And then if we added additional poles, let me go back here, such as this, put coils on them. We could then commutate these fields, and that would in effect let this thing rotate. And that's how a motor works. In the electric world, we have Ohm's law. We also have another law called Hopkinson's law, which deals with the magnetic world. So just as we have E, voltage equals current times resistance, in the magnetic world we have force equal to the magnetic flux times reluctance. This is magnetic flux, and this is reluctance. We have our circle equation here, EI over R, and in the magnetic world we have F, V, or R. In the electric world we have E equals to voltage. In the magnetic world, F equals, we called it magneto, motive, force, aka MMF. Continuing this analogy, in the electric, I equals current, and phi equals magnetic flux. Resistance it converts to reluctance in the magnetic world. So if we and that is Ni, which is the turns, number of turns times the amps over Weber. So this is turns, this is amps over Weber. Looking at a simple circuit, a voltage source, we have a current through a resistor. In the magnetic realm, we have a force, and a current. This is in a flux, I should say. If we draw a circuit, an electric circuit in the physical world, we have a battery, we have resistances, and we have wires. In the mechanical world, we have a core, we have a rotor, and air gaps. So, and those are all reluctances. So we have 4 reluctances, just as we have 4 resistors. So it's core and 2 air gaps, here, here, and here, and the rotor. If this is an electromagnet, we'll add our coil and current source. And the turns ratio, turns times current equal amp turns and one thing to note here, that electric and magnetic circuits can be modeled using the same thought processes as you've seen here. Now let's take a piece of iron which is comprised of many small particles. Some of the particles have magnetic fields, but they're all random and there's no magnet. Now we add a coil though, and the particles would start to align themselves. They would all point in the same direction. So suppose that piece of iron is our electromagnet. If we increase the turns current, actually if we increase a current or turns, that would either one would increase the magnetomotive force here at the gap. There is a limit, however, of all the magnetic, when all the magnetic domains line up. This is called saturation, and we'll explore this more when we talk about motors. Next thing I'd like to talk about is the right-hand rule. The right-hand rule describes how the magnetic lines of force align with current flowing in a conductor. And I have this pen here, hopefully you can see it. So I put my right hand on it, my thumb points in the direction of current flow, and my fingers show the direction of the magnetic lines of flux. So if we look at it in a simple circuit of current flowing through a wire in this direction, we can see that the magnetic lines of flux basically change direction as we move along the wire based on the right-hand rule. So with conventional current flow, we use the right-hand rule. Right-hand rule. And that is when we have a current flowing from the plus to the minus. We call that conventional current flow. We also have electron current flow, which is actually the way current flows from minus to plus, which would be this way. So if you use that convention, you use the left-hand rule. So what will we be using in the course? It's basically perfectly acceptable to use either, but in this course we will use the right-hand rule. So please use that as we go forward. We can use the arrow analogy with current flowing in a wire. An arrow has a tip and it has feathers, which we call the fletching. So if the current is flowing into the page, in other words, you'd be looking at the fletching, we see that the magnetic field generated is in this direction. If the wire is flowing, the current is flowing out of the wire, out of the page, the magnetic field is the opposite direction and looks like this. Now let's see what happens when we put two wires together. So if we put them so the current is flowing out of one wire but flowing toward us in the other wire, what we see, the way the magnetic fields line up, is you would have the two norths together and the two souths together. So that would mean the wires would be opposing each other and trying to push the wires apart. In the second example, we have them both going into the page, and we see that now the north and south poles are together, which will attract each other, so the wires will tend to pull together. In our last example today, we'll look at our electromagnet. Let me just draw a little 3D picture here. And basically we have our coil, we have our iron, we have our gap, we have magnetic lines of flux through the iron this way, and we have a wire between the gap with a voltmeter on it. So what will happen here is if you move the wire horizontally, like let me just draw it right here, back or forth, that will induce a voltage because you're cutting across the magnetic lines of flux. If you move it in the vertical direction, you would see 0 volts. And that about wraps it up for the day, and we'll see you next time.